Hello and welcome back to Calculus 2, section 6.9, modeling exponential functions or exponential modeling. A lot of areas of human endeavor involve exponential modeling with exponential functions. We can technically venture into any discipline from charging, discharging capacitors and other electronic components, which is electrical engineering, to models with money and talk about banking, economics, and so on, to carbon dating, where we can venture into history and archaeology. We can also talk about environmental issues in terms of garbage decay, radioactive decay after any of the nuclear crisis that we had for a few times. So a lot of aspects of what we do are covered by these. And then obviously biology with terms of population and whether it's bacteria or rabbits or humans. So a lot of stuff is covered with these concepts. And before we take a look at a few examples, I like to start with those basic graphs where we have exponential function looking like this, which is exponential growth. This is where the k is positive. I'll eventually write that. And then we have exponential decay. Which is where k is negative. This value a, which I have on the y-axis, is the y-intercept. And all of these models are a e to the k t, t being time. So with use of this equation and knowing what time we're looking at, we can figure out a lot of different things. First of all, note that k is larger than 0. It's positive for growth and negative for decay. Now k equals to 0 kills the exponential function, right? Because it will be e to the 0. So it just be constant function a. All right. So that's the part. This is the basic formula that we usually write in math terms. And then we change these letters to match the application every time when we want to solve those things. So you would say population at any time t is initial population e to the kt. You would say for money that amount at the other end as a function of t is the principal times e to the rt, where r is the rate at which it's compounding. Or you would say that the mass of the object which is decaying is initial mass, which is capital M, times e to the, again, kt, and because it's a decay model, k will be negative. So I just gave you 3 examples, right? Population, and then in terms of money, and then the mass equation there, the decay problem for mass, which can be used in environmental sciences. It could also be used for carbon dating, which is history and anthropology, and so on. Not anthropology, the archaeology. There we go, much better. All right, so let's take a look at the world population. So population clock at the moment. So we're going to call this 7.37. So now, which is 2017, it's 7.37 billion. And I'm going to see let's find what year in the past, because we can always get the data. Something that is not too far away. 1995? All right, so let's find the population in 1995. $5.7. And where do we want to look in terms of the future? 2020? That's in 3 years. 2030? So this is the information. There's no calculus in this thing, but we will add calculus at the end once we're done with mathematical modeling and answering this question. All right, so what am I going to do here? And this is, guys, this is very important. If you get this part, the rest might be much easier for you. I am going to say that the world begins in 1995, and I am setting that as my t equals 0. So I will pick the lowest year as the beginning of time, which immediately makes this 5.7 billion to be the initial population, because we are starting from there. Now, this one is immediately t equals what? 22. And this one is immediately t equals 35. Awesome. So now, what are my points of interest for this problem? I have a point 0, 5.7, from where I know that the initial population is 5.7, because at time 0 is when you have initial population. I also have a point 22, 7.37, which is the current state. And I have the point where I am looking for the actual population. So now I'm going to write the mathematical model. So P equals P0 e to the kt. And I'm going to plug in P0, which is 5.7 e to the kt. I'm going to use this point. So 7.37 is equal to 5.7 e to the k times 22. Divide both sides. Oh, this is what you need the abacus to calculate these things quickly. And anytime you're dealing with exponential equations and so on, unless it's money, it's 4 decimals. And if it's money, it's 2 decimals on the final answer. Use 4 decimals in all calculations until the very end, and then you write your answer as 2 decimals because it's cents. So now we have 7.37 divided by 5.7, which gives us 0. And this is what you use 4 decimals. 1293, rounded properly, is equal to e to the 22k. What do we do now? ln both sides. So we're not multiplying by ln, we are applying ln to both sides. And now we have ln of 0.1293, which is negative 2.0456. And on the other side, we just have 22k. So we take the number divided by 22, and we have our k. negative 0.09298. I have 4 digits there after all these zeros, which is, as I said, what we want. And now I'm ready to write mathematical model. P at any time is 5.7 e to the negative 0.09298 t. And I'm going to box this because this is the math model that allows us to calculate population in the future, in the past, or whatever. Yes?
I divided 7.37 by 5.7 and I got 1.29 instead of 0.129.
Oh, I missed the point. Oh, wow, yeah. All of these numbers are now different. Well, that's okay. Oh, you write with pens? Well, you shouldn't. Oh, wait, I completely didn't catch that. Wow, the population is growing and I got negative k. Holy nightmare. This is awful. The class is over. I'm going to go and cover myself in shame somewhere. Like no one will ever find me. Or they will. Holy nightmare, this was terrible. So we'll keep this this is not a this is not an error, this is not an oops thing, this is just stupid. So we'll keep this between us and the internet, okay? Yeah, luckily I have like 1.5 views, so that's good. Yeah, that half is gonna write it out for the world. All right, so there it is, mathematical model. Now I'm going to emphasize that k is positive, right? Because we are expecting population to grow. It's a growth model. So now you want to know what's happening in 2020, which was t equals 35. So how much is, so for year 2030, we will plug in 35 for t. And let's see, 5.7 e raised to the open parenthesis 0.01168 times 35. Yeah, my ability to type in the calculator has diminished. Now I'm keeping 2 decimals because the input values were 2 decimals. And we see that we are projecting to have 8.58 billion in 2030. Okay. Yes. In your head to the 12th decimal, and then you round it correctly. I don't know what they do at NGIT and Rutgers because there's no policy of no calculator whatsoever. You have a no graphing calculator policy. You can bring the scientific one. You know, the one that has E's and LNs. Is that the one? Right? Is that the one? Yeah, you guys can lift those and everyone can see. So that's the one that has, right? There's no graphing capability on that one. I like TI-30 TX, whatever. All right, we didn't do any calculus yet. So all of this you were supposed to know already, 100% of it, because this is the typical pre-calculus 1 problem from chapter 3, section 5. So 100%, we did not add anything to it. Now, calculus. I want to know, here, calc. Is this model good on long run? Like, can I keep using this model till the end of days? And the way to check that is, hey, look at that. So what you do is you take the limit as time goes to infinity, right? 5.7 is 0.01168 t. But since k is positive, we know that the limit is going to end up being infinity. And we know that the limit gives us the y values, right? And in this case, y value is the population. So this says what? The population will be? Yep. Is that good? Hell no. Right? So what we discovered with this particular calculation is that this model is okay to use locally, a few years ahead, few years back, but you can't keep this model as the model of population till the end of days. And then you keep tweaking. All of this stuff comes from differential equations. You keep tweaking this into logistics model and so on. So just to support this idea, guys, this is how the graph looks like, and this is where your 5.7 billion is, and this is where your time goes to infinity, which you can see that the population is trying to go to infinity, right? So it is a bad model for all of them, right? But it's good locally, right? You take a little sliver over here, and it's fine, right? We're gonna be a few 100,000 here and there, but just texting fixes that. Well, rather well, we have no autonomous cars yet. People are afraid. All right. So how do we fix this? Well, as I said, there's a logistic model and so on. We're not going to cover that here, but eventually in differential equations, you are going to see a model that starts at P0, grows, and then flattens like this. And that flattening, when you do that limit, you reach carrying capacity K, which, as I said, depending which paper you are reading, is the carrying capacity of the planet, which means the maximum amount of population that the planet can withstand in terms of resources. We're talking food, energy, space to live, and all of that stuff. And we know it's not infinite. Yes?
I don't know if this is the correct application for that, but would the odds of having a certain amount of money be related to that? Like, it's very rare to have $1 million, but going from like $1 billion to $2 billion is like easier. So I'm thinking like some kind of probability distribution for that.
Well, the way I see it is like that movie, all of those people that have that kind of money is going to move to Mars or something.
So when they leave over there, don't the whole thing get poisonous? One is based on you having money.
But that's only 1%.
Exactly. So if they move somewhere else, the money they have is going to be worthless at the end. Unless they leave with like something that's valuable to them.
Yeah, we can discuss that at some other point, but yeah.
What movie?
The one that starts with E, I can't remember. Yeah, that bald doctor.
It has who?
I don't know by names. I don't.
No,
I don't
like
pay.
what did you describe the name? Like something about a fall or something?
Yeah, it's the one that girls like. I don't know.
I've never seen it, but I've just
Ask them. I don't know.
to Mars or wherever.
I just know that movie starts with E. The name of the movie has this thing in space. There you go, Elysium. Thanks.
What was it?
Elysium.
Elysium.
They're not in mice, they're just on a space station.
Well, yeah,
Yeah.
it was that Woodcock guy, the director.
Yep. All right. Now, the next part of the calc. Oh no, that's cluttering it more because aliens coming in. We can fix this. All right. So going on with still with the problem is, can we figure out how many people are we going to add this year? Just this year. Yeah, how would we do that? Yes? Yeah. Ta-da. So we can. Oh, I don't have the ta-da anymore. Too bad. Sorry. Moment is lost. Please forgive me. So yeah, you can find how many people are going to be added in 1 year if you integrate from 2016 to 2017. You can also find the rate of change of people by taking the derivative for a particular year. Yeah? So all of the concepts that you learned earlier, you just have to figure out which one is the one to use. And we also have the averages for integrals. So you know that each year, right, the more people, the larger the population, more eHarmony couples, the more babies, the more population, and it just rolls like that. I don't know how it goes. Okay, so now we are moving on to something else. The other type of problems would be decay problems. So this was a growth problem. Now we're going to take a look at decay problems. I have my favorite problem. Anyone was in my pre-calc 1? No. I don't have anyone from my pre-calc 1 over here. Good. So this is my favorite because it shows how we grow as a species. So back in the day, we're talking 1943, there was the first teeth whitening toothpaste came on the market. The name was Doramad. Anyone knows about Doramad? No? Here it is. Dude. So Doramad is the first tooth whitening toothpaste that was sold, and what's so awesome about this toothpaste is that the substance that was whitening teeth was a radioactive element called thorium-229, the isotope 229, and people brushed and then died. Yeah. So you have all of this wonderful, wonderful, wonderful advertisement, and then they say, don't use it, right? Yeah. So let's do the math. We have everything over there. They started producing this, and I think 1943 shut it down within 2 or 3 years. So it's safe to assume that everyone who brushed with this is at least 70 years dead, right? Usually 80 years dead? 80 years dead. 1943, 70 years. Yeah, 70 years. Let's use 70. So what I want to figure out is percentually how much of the thorium that they put on their teeth decayed and how much is left. And we can figure that out by using cool math. So let's do that. So decay problems. So first of all, there is a concept of half-life. Maybe I should do this in red because it's important. Half-life is the time in which mass of an object will be divided into, will decay to half of its original value. Initial value. So as you are thinking about, so t equals lambda, it's time. So now what I have here is the model for these exponential things. And if I am to use lambda, which is the time, we see that these m's drop. You apply ln to both sides, in which case we come up with the formula ln of 1/2 is equal to k lambda, from where you can either solve for lambda as ln of 0.5 over k, or you can solve for k, depending what you need, ln 0.5 over lambda. So if you have half-life given, you can find k. If you have k given, which is possible, you can find what the half-life is.
How did the ends cancel?
You divide both sides by m, big M. Right? Bueno? All right, so let's do the problem. So what do we have? We have, let's say, 1947, when everyone died, say, and we have certain amount of doramad used, and then we are trying to see what is the percent of doramad left of thorium, TH29 left. So that's what I want to know. So they applied certain amount, and that makes deposits on teeth, obviously. And then let's see how much is left after 70 years. Now, if you browse the internets, as they would say, you would come up with the half-life for thorium-229 of 7,340 years. Now, this means that it has to pass 7,340 years for half of the amount to go away. Then you have to wait another 7,340 years for half of the half to go away, and so on. Awesome. So let's do it. We already know the formula that the K is going to be ln of 0.5 divided by 7340, which, according to my calculations, is negative 0.0009443, which gives us math model that the mass at any time t is equal to initial mass times e to the negative 0.000943 t. This is the math model for thorium-229. Now I'm looking for percent. So looking for percent left after 70 years. Percent of what? Percent of original amount applied. Not everyone applied the same amount. Some people brushed 17 times a day. Yes. So the way it goes is that percent of the original amount is equal to the equation. You know the word of means multiplication. And lowercase p is the unknown percent. So this m will drop. And we are going to plug in 70 over here. So I get that the percent that it's left is e to the negative 0.00094443 times 70, which is equal to, so e raised to the open parenthesis answer times 70. 0.936, which translates into 93.6%. These are the best looking skeletons out there, right? Yes.
When you calculate 11.05 divided by 7,340 minus 9.4 is 10 to the minus 6.
No, 4.
Okay.
(9.4 to the negative 5).
To negative 5? My calculator gave me negative 4. Let's see. ln of 0.5 divided by 7340. Huh, it is. All right, put in one more zero. There's going to be one more zero floating everywhere. And that's it. All right. It should be, it could change a little bit, but it's going to be 97% maybe.
99.
99%? Nice. So e to the answer times 70. 99.3%. Nice. All of it is there. Well, that decayed. 70 years lost 0.7% in the thorium deposits. That's how insignificant we are. Okay, so that's what other types go on, figure out what's the half-life to decompose a bag, like a garbage bag, the black one, or the ShopRite bag, standard plastic bag. How long will it take to decompose? I actually had this maybe 5 years ago or so with the math club. We worked on the decay of one of those markers for the board, one of these guys. That's how I know that they're 16 grams, because we went to the chemistry lab and we measured a whole bunch of these, and they all averaged to 16 grams of mass. And then figured out what type of a plastic is used, and then what's the half-life for that to decompose, and go on do the research. I won't tell you. It's a really fun exercise. So, did we also for ShopRite bags? So there is a lot of these cool things you can do. Environmental sciences are going to deal with this in terms of radioactive decay after any kind of nuclear catastrophe, which is why we need fusion ASAP. And then also garbage disposal, right? All of that garbage decay is that problem as well. Now you can also talk about compost and all of that kind of stuff, which is again form of decay. Medical research, decay of flesh, right? We have that as well. Different diseases and so on. It's used there. And also, yeah, medical field, huge application, guys. Anytime you take a pill, it's going to metabolize in the body this way. So you actually have, anytime you look up any kind of a drug, you are going to end up looking into, you will also get the half-life of it. And you can use half-life to figure out the dosage on your own. I actually had in one of my classes at one point a problem where I believe I did either use Advil or aspirin or something, gave the half-life, and you see that the doctors recommend every 4 hours, and the calculation ends up being 6 hours, and the calculation will end up being like 6.2 or 6.3 hours. These things are not, they don't have a whole bunch of humans that they test on this and they say, oh my God, they took every hour, so they're dead. These took every 2 hours, they're all dead. No, you calculate these things, right? And then when you are ready after 5 years to do human trials, then you don't have 5 out of 10 groups dying. Here. So if you go to your Mathematica, oh, you can't see it, which is actually, you have this watered down version called Wolfram Alpha, and you type any type of drugs there. I use Advil. You get everything that exists on that drug. And that's for all drugs. See, you have the chemical composition, you have the Lewis structures and all that. If you want to cook this stuff at home, you can. And they tell you how it interacts with other drugs and all other chemicals, and there it is, biological half-life 1.9 hours. See that? You have this listed for every drug. The problem that I did for thorium, the problem that you do for garbage, the problem you do for carbon decay, for the carbon dating, all the same calculations with half-life, including this. So when you take this and do the calculations, you will find exactly what the dosing is and how it works. So this section has insane application. Not even to go into electronics and charging and discharging capacitors, talking about the batteries, the storages, what Tesla does, and not Nikola Tesla, but Tesla, Elon Musk, and this kind of thing. So this is the section that makes you money. The 6.9 is the section that is actually your job as the engineer, as the researcher, as the lab technician, or whatever you want to go for. That's what you do, these kind of calculations. And then you take limits. You take, so by figuring this out, that the drug is going to metabolize on exponential decay rate, how long do you have to wait for a single pill to metabolize 100% of it?
Bravo.
Why forever?
Oh.
Because half of the half and 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 half of the half. Guys, decay graph does not cross x-axis ever. So this is when you take a 200 milligrams right here, and it's gonna go in time, and it's never gonna hit 0 milligrams, which is here. It's exponential function. So it's gonna go, and it's gonna take forever for it to get. You carry in your system everything you ever took since day one. Yes?
No, that makes sense actually.
There we go. Perfect. So, sorry, but such is life. It's gonna wean off a little bit. But you got enough already. But you're in your 20s, you got it. Fine. So all of these problems work the same way. Okay. You have two examples. Now, what else? Calculus-wise, again, for this problem, we just took the limit as time goes to infinity to see that we actually have to wait infinite time for the drug to metabolize it. We have to wait infinite time for all of the thorium to go away. We have to wait infinite amount of time for all of the garbage to decay. It is exponential decay, and it's 0 only when it reaches infinity. Next, integrals and derivatives. Anytime you have mathematical model, which is the one that is boxed in the lecture over there, you either take the limit to see what's happening as it grows to infinity, much more on that in differential equations, or you differentiate that to see the rate of change. You can calculate how much was lost, right? What's the change in amount within a year, right, for a particular time. So how much thorium was lost in year 1? How much thorium was lost in year 2? Do the integral to figure out how much thorium was lost across 5 years. Derivative can't do 5 years, right, because derivative is snapshot in time. You do it one point at a time, what integral takes, right, and you do the average integral, 1 over b minus a, integral a to b, and then that formula, to figure out over time. Now, this is a joke to integrate, because that's a number, right? How much did you put? You took a pill of 200 milligrams, 250, 500 milligrams. So that's a number. That's a number. The integral of this is this divided by that, times that. And then you compute from 0 to 3 or 3 to 10 for t. So in terms of calculus, the level of skill that you need is nothing, because you're just either differentiating basic exponential function or integrating basic exponential function. Yeah, it just has messy numbers, whether we're going to have an extra 0 or not, which makes a difference, but still. So that's the part on 6.9. The next time we do, let me just say bye to stream and all of the thousands of viewers that always join us. Thank you.